This is chapter 9, and this chapter is called Stoichiometry. Stoichiometry, okay? It's a big fancy word. Stoichiometry means putting quantities to chemical reactions or quantifying chemical reactions, okay? When I say that, what do you think that means? What does quantifying mean? Putting what? Not necessarily make larger.
It's how many there make more.
Even more general.
Counting the quantity?
That's pretty close. Quantifying just means we're talking about the quantity, right? We're putting a quantity to the chemical reaction. So far, all we've done is build the reaction, right? All we've done so far is say lithium hydroxide plus magnesium nitrate yields whatever, right? But now we're going to actually put numbers to it and say, if I have 10 grams of lithium phosphate and I add in 30 grams of magnesium hydrate, what's going to come out, right? And how much of that is going to come out? That's what we're looking at with stoichiometry. We're going to quantify chemical reactions, okay? So we're going to put numbers with it. The first thing we've got to introduce is something called a mole ratio. Mole ratio, okay? Mole ratio is a conversion factor that helps us relate the number of moles of any two substances. So this is important. It's a conversion factor. Just like molar mass is a conversion factor, molar mass helps us convert between what and what? Grams and moles, right? Molar mass helps us convert between grams and moles. What does Avogadro's number help us convert between?
Molecules and atoms and moles.
Yep, molecules and moles, okay, or atoms and moles. And so mole ratio is also a conversion factor, but it helps us convert between moles of one substance and moles of another substance, okay? So far, all the conversions we've done have been of a single substance. We've gone grams of calcium to molecules of calcium. Oops. Okay, but now we're going to go maybe grams of calcium to grams of nitrogen or grams of something else, right? A completely different compound. But we have to do that with what's called the mole ratio. So I want you to think about this for a quick second. If I have 1 gram of hydrogen and 1 gram of oxygen, do I have the same number of atoms of both of those? No, right? Because a gram of hydrogen is a whole mole. That's how much a whole mole of hydrogen weighs. Would we agree? But a whole mole of oxygen weighs 16 grams. So if I have 1 gram of oxygen, I only have 1/16 of a mole. So I don't have the same number of atoms in that. Does that kind of make sense there? A gram of oxygen and a gram of hydrogen, they have the same mass, but they don't have the same quantity. You see the difference? A gram and a mole are not the same thing, right? A gram is weighed, and a mole is counted, right? A mole is a certain number of atoms, 6.022 times 10 to the 23rd atoms. So let me just write it out here, okay? A mole of oxygen weighs 16 grams.
So it's like if something had the same weight, like if they weighed the same but it was a different amount.
Right, that's right. If I have 10 objects that together weigh 2 pounds and I have one object that weighs 2 pounds, they have the same weight, but there's not the same number of those things. Okay? So oxygen weighs 16 grams. A mole of it would mean I have 6.022 times 10 to the 23rd of those oxygen atoms. 1 mole of hydrogen only weighs 1 gram. But it also means I have 6.022 times 10 to the 23rd of that thing. So I can't compare the quantity of hydrogen and oxygen in grams. I can't say that 1 gram of oxygen is the same number of atoms as 1 gram of hydrogen. They have the same mass, but they don't have the same number of atoms.
What if there's 16 grams of hydrogen?
16 grams of hydrogen. Nope. They would have, their mass would be the same, but this would be 16 moles of hydrogen. So there would be 16 times as many atoms as there would be of oxygen. Okay, so we can't compare 2 different compounds in grams. We have to compare them in moles. Okay, because moles tells us the quantity, not the weight, but the quantity. That's what we're really looking at. All right? So if I look at this reaction, okay, we're going to do a little review here about types of reactions. So first of all, tell me what type of reaction it is. Single displacement, double, combustion, what is it? No. I didn't list a couple of them.
Decomposition.
I think it's decomposition. Okay, I think it's decomposition. Okay, because I start with a complicated molecule or a complex molecule, and it gets broken down into two smaller molecules. So let's talk through what this reaction says. It says if I start with 2 moles of potassium chlorate, it will break down and form 2 moles of potassium chloride and 3 moles of oxygen gas. That's what will happen if I have 2 moles of this substance. Now let's say, what if I start with 4 moles of this one? How much of my products can I form? If I start with twice as much as I need, how much of my products can I form? 4 moles of that one, and how many? 6 moles of that one, right? It's all about ratios, all right? If I start with, let's say 10 moles of this one, how much of this product could I form? I'm supposed to have 2, but I have 10 instead. I'm supposed to have 2,
10.
but I would make 10. I'm supposed to have 3. How much could I make? 15. You see how I have 5 times more than I need. Okay, but the ratios are all the same. Do you see how that works? That's what we're going to start doing, but I'm going to give you a process to be able to predict these numbers. You're not just going to have to look at it and see it. I'm going to give you the process of how we're going to do that, okay? So let's go ahead and balance this reaction real quick, and then we're going to answer a couple questions that go with it, okay? We're going to answer a couple questions about mole ratio. So I'm going to balance the reaction. I'm going to start with nitrate here. I see that I've got 2 nitrates. I'm not going to make my full list to balance it, right? If I see I have 2 nitrates, that automatically tells me I'm going to need a 2. And then what other element does that affect? Silver. And so I need to come over here and put a 2. And then is that done? We're balanced? I actually think so, right? I've got 2 nitrates, 2 nitrates, 1 copper, 1 copper, 2 silver, 2 silver.
Does the not apply to the copper?
The 2 only applies to what's inside the parentheses there, okay? So as we get better with balancing equations, you're not going to have to make the list every time, right? I picked a place to start, and then I bounced back and forth until I got a finished balanced reaction, okay? You don't have to make the list if you feel comfortable with that, okay? So now let's ask this, or answer this question here. What's the mole ratio between copper and silver? Right here, this was a 2 and this was a 2. The mole ratio between copper and silver. All right, what's the mole ratio or the coefficient that should go right here? 1. And what is it for silver? 2. So, yeah, it would be like 1 to 2. So I would write it, I would say 1 mole of copper to 2 moles of silver. Sometimes in math, you write a ratio with the 2 dots, right? But with these, we write them as kind of like fractions because that's how we're going to put them into our T-chart. Sorry, I'll put it up a little higher. 1 mole of copper to 2 moles of silver, okay? With this chapter, we're about to enter like T-chart city, okay? We're going to have T-charts all over the place. Not necessarily that are super difficult, but we just have to do several of them per problem sometimes. Okay, so we're going to set up that mole ratio so that it can go into a T-chart really easily.
What was the mole ratio for the first reaction?
We didn't answer a specific question about the first reaction. Did it have it on there?
Yeah.
What did it say?
What is the mole ratio between...
KClO3?
Oh, I'm sorry. Okay, so KClO3, it would be 2 moles of this to 3 moles of that. It comes right from the coefficient that's in front. Okay, sorry, I didn't mean to skip that one. Start practicing some stoichiometry conversions, okay? And we're going to start with the simplest one. which is a mole to mole conversion. Okay? This is where we take the amount of our given substance in moles and we get our answer in moles also. These are the easiest type of conversions here. I'm going to go ahead and balance this for us just to speed it up. And I actually think it's just balancing with a 2 on lithium hydroxide.
Was our mole ratio between copper, Cu, and Ag 1 to 2?
Yep. Okay, sorry. Here's our balanced reaction here. Okay. The question asks us, you might need to write down this too on your equation, right? You want to make sure you have the coefficients all right, okay? This says how many moles of lithium hydroxide are required if we want to react with 20 moles of carbon dioxide, okay? Do you kind of realize how important the naming part of it is now? Why we did the review with naming? We've got to know what lithium hydroxide is, right? You've got to be able to go to your problem and figure out what lithium hydroxide is, okay? So when I'm going to do the problem, I'm going to kind of highlight some things I'm looking for here. The question asks me how many moles of lithium hydroxide. So I'm going to come up above here and write my question mark, and I'm looking for moles. Okay, how many moles of lithium hydroxide are required to react if I have 20 moles of CO2? I'm not going to change the coefficient in the problem. I'm just writing it above to kind of help me focus in on what I'm looking for in my problem. Okay? Now I'm going to actually do the calculation, and I'm going to do it in a T-chart. Okay? Types of reaction. Okay, we can talk about that, but it's a double displacement. That's not what we're really focusing on right now. Okay? I am going to start my T-chart always with what? What I know, right? I'm going to start with what I know. So 20 moles of CO2. And I'm going to make my T. Okay, so I want you to do this with me. 20 moles of CO2. Now, what automatically has to go down in this bottom right-hand corner? Okay, moles of... It's got to cancel. So we got to go moles of CO2 right there. Okay? Now, we're going to go, we want to end up in moles of lithium hydroxide. So it can go above. Moles of LiOH. Okay? This step right here is called the mole ratio step because it is mole to mole. Okay? This is the only step that you can change from one compound to another. Okay, I want you to write that down extra, like on the top of your slide or to the side or whatever. Okay, this is called the mole ratio step. And it is the only place in your T-chart you can change from one compound to another. So that means I couldn't go grams of carbon dioxide to moles of CO2 on top. I could not do that. It has to be mole to mole. So this step right here is called the mole ratio step. So you might even want to highlight that as well on your problem, okay? Okay, so now I'm going to go put my numbers in. Now, up until this point, we've said that moles always gets the 1. Now we're backtracking on that a little bit, okay? Because now in the mole ratio step only, the numbers come from the balanced chemical equation, okay? You're going to go find their coefficients and put them directly in the chart because it's all about the ratio, okay? So the number of moles of carbon dioxide that comes from the problem is what? 1. And what's the coefficient that's in front of lithium hydroxide? 2. Okay? So I'm going to look at my units now, double check that they cancel. Carbon dioxide moles of carbon dioxide. I'm left with moles of lithium hydroxide. So that means I multiply across the whole top, divide by the whole bottom, and I get moles of LiOH. H2O2 breaks down to yield H2O and O2. So if I balance this is going to put me at 1 there, 2, 2, 1. Right? I've got 4 oxygens on the right, 4 oxygens on the left, 4 hydrogens, 4 hydrogens. Okay. So this says how many moles of O2. So I'm going to come up here and make a little question mark above here because I'm looking for moles of O2. Will result from the decomposition of 5 moles of hydrogen peroxide. Now, do you know which one hydrogen peroxide is? What'd you say? Yeah, how do you know that? Yeah, that's right. That's exactly right. By process of elimination, I know that this one has to be hydrogen peroxide, right? I know it's not this one, and I know it's not that one, so it's got to be the third one. So you can use process of elimination. You don't have to necessarily know how to name every molecule. You just got to know how to be able to figure it out, okay? So now we start our chart with what? What we know, H2O2. Our goal is to get to moles of oxygen, but I'm going to cancel moles of H2O2, and I'm going to go to moles of oxygen. Now, what do we say this step was called right here? It's called the mole ratio step, okay? And in that step, we get our numbers directly from the balanced chemical equation. Okay, we get these numbers directly from our balanced chemical equation. So tell me, what number is going to go with H2O2 right here? 2. Very good, because it comes right up here. And what number is going to go with oxygen? A 1, right? Because that's the coefficient that's laid out right there. And that's it. Okay, cancel moles of hydrogen peroxide. I'm left with moles of O2, which means I'm going to have 2.5 moles of O2 that I can produce from that decomposition. But I'll just balance it for you because this one is, so 6, 6, and 6. All right, this one is now taking it one step further and asking us for grams. So now we're going to look at relationships from grams and moles. All right, so we've got to take our T-chart one step further, and I'll show you what I mean when I say that, okay? It says, what mass in grams of glucose is produced when 3 moles of water react with carbon dioxide, okay? So I'm going to zoom in on what I know. I know I have 3 moles of water. And what am I trying to find? Grams of glucose. So tell me which one we know glucose is. It's got to be that one, right? So I'm going to put question mark grams. That's my goal. Question mark grams. Okay? I always start my chart with what I know, what comes from the problem, okay? So I'm going to start with 3 moles of water. And I'm going to draw my T.
Why is there
A 1.
in parentheses after the
It's an L for liquid.
Oh.
Yeah, sorry. I don't know why I stopped putting those on, but the G and the L just mean gas or liquid. So I started with what I know. Moles of water has to get canceled, so it comes right down here. Now, am I concerned about grams of water? Do you think I should go to grams of water? No. My overall goal is to end up in grams of glucose. So if my overall goal is to be in grams of glucose, what do I need to go to?
moles of glucose.
There we go. Moles of glucose. Because the only time I can switch compounds is when it's in the mole ratio step. Okay, sorry. This is the mole ratio step, right? I'm going to go from moles of water to moles of glucose. Remember how I said it's going to be important for us to keep our name of our compound in the chart, right? Now it's really important because I might have 2 different names. I might have 2 different compounds I've got to pay attention to, okay? Now I'm going to keep my chart going because I don't want to just end up in moles of glucose. I want to end up in grams of glucose. So I cancel moles of C6H12O6 and I put it in grams of C6H12O6. But now we're back to a part of conversion that we know where moles always gets the what? The 1. So here moles gets the 1. What's going to go with grams? Molar mass. So let's go ahead and calculate that. We'll fill in our numbers for the mole ratio here in just a second. But molar mass would be 12 times 6 plus 12 plus 16 times 6. 180 grams per mole. And then let's fill in our numbers here for our mole ratio step. Right? Here's the mole ratio step. Tell me what number is going to go with glucose. 1. And what's going to go with water? 6. Very good. Okay, tell me, what questions do we have about filling our numbers into our chart here?
There isn't any time you're going to need Avogadro's number.
There will be. We're just not there yet. Okay, we're going to go, we're going to work with grams first, and then we'll go work with atoms later. Okay, right here. This one is molar mass. So I calculated molar mass of that C6H12, okay? All right, so now we multiply across the whole top, divide by the whole bottom, and we're going to get, let's see, I think 90 grams of glucose. How many grams of water are produced if 2.2 moles of NH3 are combined with excess oxygen? Okay, so my equation's already balanced. I want to start breaking down the problem to figure out what's it really asking me. Okay, it's asking me how many grams of water are produced. So that's my final goal, right? I want to look for grams of H2O.
Where's this water coming from?
Well, when these atoms break and rearrange, they form water molecules and NO molecules. Right, that's the whole point of a chemical reaction, right? These atoms are going to rearrange and form something new. So I'm looking for grams of H2O. I start with 2.2 moles of NH3, and it says it's combined with excess oxygen. What does excess mean? What's excess mean? It means extra. That doesn't affect our problem at all, so you can just get rid of that. Okay? That information is not important to us right now, okay? I'm going to start with what I know. 2.2 moles of NH3. All right, what's got to go here for me to cancel? What's got to go on the bottom right for me to cancel? Moles of what? Good. Moles of NH3. And what am I going to go to right up here? Good. Moles of water. Okay. I know this has to cancel diagonally. This has to go to moles of H2O because that's the only place I can switch to a new compound. Then I'm going to get rid of moles of H2O and I'm going to go to grams of H2O. Okay, so now let's go put our numbers in. In the mole ratio step, what is water going to get? H2O, that's okay. H2O is going to get a 6, and NH3 is going to get a 4. They come right from the balanced chemical reaction. Then we come over to this step, and we say moles always gets the 1, because we're back to a regular mole to gram conversion. So moles gets the 1, and then grams gets molar mass. So do you know the molar mass of water? 18. Good. If you don't have your calculator and periodic table out yet, please make sure you grab that. So we asked a question that says, why does this H2O not include a 6? Because there's a 6 right here, right? Why is it not 6 moles? Well, the molar mass we give is only for 1 mole of that compound. And we took care of the 6 by putting it here in the mole ratio step. So if you were going to put 6 moles equals 18 grams, that wouldn't be true. right? Because that's not how much that's not how much 6 moles of water does weigh, right? And if we put a 6 down here, then that would just end up canceling and we wouldn't have our true ratio happening. All right, so we multiply across the whole top, divide by the whole bottom. Please plug this into your calculator. I want you to make sure that you feel good about plugging it into your calculator. Get the muscle memory down for the T-chart because we're going to be doing them a lot, okay? So multiply across the whole top, 2.2 times 6 times 18. I hit enter there. Divide by the bottom, which is 4. And that means I got about 59.4 grams of water. Is that what you had? 59.4 grams of H2O. Okay, try this one on your own, and then I'll get it maybe up on the board here in just a second. Now, I will tell you, it does not matter that we are going from product to reactant on this one, right? We're starting with information we know about a product and trying to figure out information in a reactant. That makes no difference, right? It does not matter how we're doing, that we're going from product to reactant. Okay, sorry. Okay.
It's
not my fault there were 50 girls in the background.
Okay, so O2 is going to get what number is O2 going to get? 5. Water's going to get a 6. Moles here gets a 1. And what's the molar mass of O2? 32. Did you remember to put 32, not 16?
Yeah.
I'm not seeing any reactions. Did we remember to put 32 or did we put 16? Okay. O2. What's it called? What's this O2 called? O2, H2, N2. What are those called? That have to exist with a buddy.
Oh, a
There you go. Diatomics, right? And how many diatomics are there? 7. Good, because they make a 7 on the periodic table. They make a 7. All right, multiply across the whole top, divide by the whole bottom. 0.3 times 5 times 32 divided by 6. I got 8 grams.
I had 7.9.
So this is as big as our T-chart's going to get. We're going to add one more step to it, okay? Where we're going to start in grams of one substance. We're going to work grams to moles to moles to grams, okay? Grams of one to moles of that one. Then you switch to moles of the other. Then you go grams of that one, okay? So you're going to have 4 kind of parts to your T-chart. That's as big as they're going to get. But the process is still the same. You know how to convert grams to moles. You know how to do the mole ratio. You know how to convert moles to grams, right? It all works the same. We're just putting it together now, okay? Yes, this is the question that we're working on. Oh, they're all the same formula. Is that why you're getting tripped up? Okay, how many grams of NO is produced if 12 grams of O2 is combined with excess ammonia? Okay, so let's figure out what's happening. What are we asking for here in our problem? Grams of NO. So we're going to make our question mark grams. 12 grams of O2. We're starting with 12 grams of O2. Okay, so now it's a little more complex to try to take a guess on our final answer, right? There's not really a way we would be able to take a guess at that. Okay, because mole ratio has a factor. What are they called? Molar masses have a factor, right? These things play into how much ammonia is going to be formed. And so how much nitrogen monoxide is going to be formed. So it's not as easy to take a guess. With excess ammonia, do we care about that part? No, that doesn't affect our problem right now. Okay, so let's start our chart with what we know. 12 grams of O2. Now, for some of you, it might be helpful to kind of map out where we've got to go. We've got to go from grams of O2 to moles of O2 to moles of NO to get to grams of NO. Right? Because the only time we can switch is when it's mole to mole. Okay? So we're going to do that in our chart. We're going to go grams of O2 to moles. of O2. And now we're kind of right where we started, right? In our previous problems, we like started with this step, right? All we did is added one at the beginning. Now I cancel moles of O2, and I've got to go moles of my new thing, which is NO. And then I can cancel moles of NO to go to grams of NO. You see how we're still just canceling diagonally? Right? But what we've got to pay attention to is what's our next step. All right, what's going to get us moving forward? What questions do we have about putting in our units there? All right, we got rid of grams. We've got to get to moles. This is our mole ratio step. Now we're going to finish with moles to grams. So now we can put numbers in.
When do you find the atomic mass?
Atomic mass always goes with grams. So whenever we see grams, we're going to have to find molar mass there. Yep, good. Okay, so let's put in our numbers. Right here, moles gets the 1. And what goes with grams? Yep, molar mass, and for O2 is 32. What did we say this step was called?
Ratio.
The mole ratio step. Okay, and these numbers come where?
Directly from the.
Right, these numbers come directly from our balanced chemical formula. So oxygen gas gets a 5, and nitrogen monoxide gets what? A 4, good. Now back over here, we're converting between moles and grams, so moles goes back to getting a 1. It does not get its mole ratio. We only put the mole ratio step in once. Okay, so you only take the coefficient one time. Molar mass of nitrogen monoxide is 14 plus 16, so 30. And then we do the math. If you want to check your units, you can. Right? I canceled grams of O2. I canceled moles of O2. I canceled moles of NO, and I'm left with grams of NO, which is what I want.
On this, would you do
Add the hydrogen to.
Learning the names.
Well, I never even. No, it's not.